So next up, we have Nikita, who's going to be presenting the medium is the message, how secure messaging apps leak sensitive data to push notification services.
Oh, perfect. Hi everyone, my name is Nikita Samarin. I'm a PhD candidate at UC Berkeley, and I will present our work on how messaging apps leak sensitive data to push notification services. Before I begin, I just want to see a show of hands here. Who uses encrypted or secure messaging apps like Signal, WhatsApp, Viber, things like that? Okay, well, you might want to wait until the end of my talk to see if the app that you use is vulnerable to this vulnerability. Let me take a few steps back. So I'm sure you're all familiar with the concept of push notifications. These are small messages that pop up on your device when something happens, and they display information from apps even if they are in the background. Different platforms offer support for different push notification providers. So for instance, on Android devices, which I will discuss in my presentation, Google's Firebase Cloud Messaging service provides support for push notifications. Know that for other platforms, it's going to be similar. For instance, for iOS devices, Apple provides support for push notifications on their platform. Let me introduce to you the key actors involved in the process of delivering push notifications. So we have the developer who controls the app server. We have the Google who provides the push notification service. And finally, we have the user who is running the client app on their Android device. So before the developer can even send the push message to the user, first, the user has to register with the Google Push service. So when the user launches the app for the first time, the client app sends a request to the Google's push service, requesting a so-called push token that's going to be connected to their device. Google responds back with the push token that the client app then sends to the server that can store for later usage. When the developer wants to send a push notification, they don't send the message directly to the user. Instead, they send the message with the push token to the Google's push notification service. Google looks up the correct device using the push token, and then it forwards the message to the correct device. The app can then display the message or perform any other action once it receives this notification. So the good part about this design is that it's efficient. Instead of having 100 apps maintaining 100 different connections for push notifications, all developers can use a single connection maintained by Google to send push notifications. Moreover, developers benefit from an easy-to-use API that abstracts away implementation details. The bad part about this is that developers effectively have to rely on Google in order to send push notification to Android devices. There are third-party service providers that offer push notifications as a service. However, for Android devices, they still have to rely on Google's Firebase Cloud Messaging in order to send notifications to Android devices. And the ugly part about this design is that this communication channel is not end-to-end encrypted by default. Therefore, any message that passes in this manner is theoretically also visible by Google. And of course, we all trust Google to keep our secrets here, right? So let me discuss the threat model. In our paper, we assume an adversary that can issue subpoenas or court-mandated legal requests. Let's say they received a tip about some user 123 on some platform. And so they go to the developer and they ask them to provide a push token corresponding to that user. The developer will most likely reply because they have to maintain a list of tokens in order to send push notifications to the correct device. Once the adversary has the required push token, they can go directly either to Apple or Google and ask to provide all information associated with this push token, which Google may also very much reply to. This information, at the very minimum, will include IP addresses. However, we have a reason to believe they may be even more than just that. And the reason I say that is that this is not just a hypothetical attack. This is actually happening and has been happening for multiple years. Back in December of last year, US Senator Ron Wyden has disclosed that foreign governments have been issuing requests to Apple and Google asking for push notification records. Since the publication of this letter, numerous journalists have identified more than 160 search warrants just in the US, going back to 2019, that either request the push tokens from app developers or request information from Google and Apple corresponding to selected push tokens. So this threat is very much real, and it's actually happening. Given this threat, we ask the following 3 research questions. First, what personal data do secure messaging apps send via Google's push notification service? 2, what mitigation strategies do developers of these apps use in order to prevent information from being leaked to the Google's push notification service? And finally, the third question, do the observed data sharing behaviors align with the privacy assurances these developers make with respect to the privacy and security of the communications on their platforms? You may be wondering why secure messages in particular. Well, there is a reason. There's 2 main reasons for that. One of them is that these are the types of apps that promise security. They promise privacy. They promise reliability. It would not be a surprise to assume that users would trust these platforms with sensitive information and assume that the contents of their communications are sensitive. Given the fact that Google might also associate push tokens with the contents, we might see the risk that is being posed to users here. The second reason is more methodological. When you receive an instant message on your device, you will most likely see the name of the person as well as the preview of the content or the entire content on your screen. And therefore, we hypothesized that many developers might simply send this information directly without applying any other mitigation strategies. And so these are the 2 reasons why we are choosing to look at secure messaging platforms. So what was our approach to answer our questions? Well, first of all, we selected 21 secure messaging apps from Google Play Store with millions of daily active users. We then instrumented the relevant methods on the Android operating system level that are responsible for receiving push notification messages from Google's push service and then passing it to the correct app. We then installed each of the apps, registered an account, and basically just sent messages to that device in order to trigger push notifications by those apps. And finally, we observed contents or lack thereof, as well as any mitigation strategies that developers might be using in order to protect them. So what do we learn from analyzing these apps? Well, on a high level, we found that almost all apps except for one rely on Google's Firebase Cloud Messaging service in order to send push notifications. The one app that did not use Google's FCM instead requested additional permissions from user in order to run a background service in the background and basically use that to receive push notifications directly from the app server. Looking at the 20 apps that do rely on Google's FCM, we found that 11 apps leaked metadata in push notification payloads. And in this case, when I'm talking about metadata, I basically mean personal information that is not the contents of the message itself. So things like user identifiers or names or device identifiers and phone numbers in the case of 2 apps. However, even more alarmingly, we saw that 4 apps leaked message contents directly via push notifications. So let me give you an example. An app called Just Talk sends directly notification contents as well as the name of the sender using Firebase Cloud Messaging, which then it uses to display the message to the user in the form of a notification. To answer our second research question, we wanted to find out if there are any mitigation strategies that developers might use in order to protect contents from being leaked to Google in this manner. So we observed 2 general strategies that developers used in order to secure notification payloads. We saw that 8 apps used end-to-end encryption of push notification payloads in order to prevent Google from reading the contents of the messages. However, only 4 secured both the contents and the metadata of the messages. And I'll give you 2 examples to illustrate this point. So first we have Telegram, which essentially sends all of the data as an end-to-end encrypted payload, which it then decrypts on the device, and it contains information both about the message as well as the user sending this data. So no information is being leaked via Google's push notification service. On the other hand, we have an app called SaveUM, which you can see also encrypts end-to-end the message that's being sent. However, it still leaks some metadata, including the sender user ID as well as the recipient user ID. We also observed another strategy, which we call push to sync. In this strategy, an app simply sends an empty or almost empty push notification, which it then uses as a signal in order to fetch securely the contents of the notification from the app server directly. Again, we observed 8 apps use this strategy, however, only 5 secured both contents and metadata. And let me give you 2 examples here again. So Signal only sends an empty notification payload that doesn't contain any information, and essentially it wakes up the app so that they can go and fetch the remaining information from the app server directly and display it to the user in a secure manner. So in this sense, no information is being leaked to Google's push notification service. On the other hand, Viber also uses push-to-sync strategy in order to protect the contents of the message. However, they still send some other metadata, including the phone number of the sender, user identifiers, and other data. Our third research question was about the disclosures that developers have and what do they promise in terms of the data being shared. So we found that all 11 apps that leaked personal information made security and privacy claims. They might lead users to believe that the contents of their communication would be safe from the third parties. In particular, we saw one app, Just Talk, which I mentioned previously, claim to be end-to-end encrypted while still leaking message contents. In particular, they used to state that all users' personal information, including messaging data, is end-to-end encrypted. Personal data is never shared with third parties. Enjoy safe and free calls. Well, I beg to differ here. So we have some key takeaways here. Although the developers are responsible for their apps ultimately, we do observe them make very predictable and repeatable mistakes when it comes to sending push notifications. In an ideal world, we would want to see push providers step up and implement end-to-end encryption by default, although at this moment we don't see enough incentives for them to do so. I will end my presentation, as I promised, with a table that outlines whether we observed data leakages from different apps. You can see if your app is vulnerable, and you can scan this QR code to read the paper. Thank you for your attention. I will now take questions. Question over here. Oh.
Hey,
Hi.
Thanks for the cool talk. So I was interested in whether you also use some alternative variants of some of these apps, because I know that Signal, you can also use it without the Google messaging push notification service, like I do on my de-Googled Graphene OS phone. Mm-hmm. And I think then the push notifications are directly sent from Signal. So did you investigate some of these alternatives as well?
Yeah, great question. So we looked at the default provider for push notifications. So in the case of Signal, it is Google's FCM. However, if there are apps that are, it's true that those apps also offer alternative messages and push notification services. In those cases, usually they would request additional permissions from the user in order to maintain the background service to be able to receive those messages. So we kind of didn't really consider that as a viable or usable alternative, I guess. There's no question there.
So thank you for the presentation. So do you know, like, if the behavior of these applications might change if the user turns off the push notifications on the device?
That's a great question as well. So when we talk about push notifications, there's two things that often people mean. The one is sort of the pop-up that you see on your screen that appears when an app decides to notify you about something. And the second is the actual message that passes from the app server via Google's FCM and then to the device. If the user disables notifications, it will only disable the former part, so the device will not display the messages. However, it doesn't prevent the push notification from being pushed through from the app server to Google's FCM and then to the device.
We'll take one last question.
Hi, thanks for the talk. I wanted to ask something that kind of leads from an earlier question. Mm-hmm. Do you know if this behavior is a a feature of Android OS or if it's a feature of Google Play. So in particular, would like Lineage OS and Graphene OS also have this kind of issue?
Yeah, great question. So what we studied was specifically Android devices that have Google Play services running, because Google Play services is the component that essentially maintains the connection with Firebase Cloud Messaging Service. There are alternative Android platforms, in particular in China, that don't use Google Play services. However, they do rely on their own providers, so it doesn't really solve the problem. It just shifts the burden from Google to another provider. But for the majority of Android apps, we observed that Google Firebase Cloud Messaging is the default provider.
Let's thank the speaker one more time.